Doctori, tutto a posto? Welcome back to a new episode of Sane C++ Libraries. That is a set of C++ platform abstraction libraries for macOS, Windows, and Linux, focusing on fast compile times, being bloat-free, simple and readable, and easy to integrate with no use of the C++ standard library and no third-party build dependencies. And I can still talk and I still don't need to take a breath. That being said, probably I can extend these principles as long as I can keep saying them just all at once. And you can look at the list of the libraries. There is a bunch of them. Of course, some of them are very simple. Some of them are more complex, like, of course, the Async library can probably be a project on its own. But today we are going to continue working on the async streams. But before going into that, please take a look at the GitHub and get in touch if you would like to know more about and learn more about the project. So let's recap what we have been doing. Let me switch to my Xcode. We have been working on this async stream. So maybe this is a little bit of introduction or a recap for what has been done so far. So if you have already seen all of the previous videos, you can just skip to the next chapter. Let's recap what has been done so far. This async stream library is kind of I don't want to say a copy because it's not a copy, but it's, let's say, largely inspired by Node.js streams, which is an abstraction to do asynchronous processing of data that can be I/O, mainly centered around I/O, even if you can put even processing that is doing like CPU work on like an external thread, like could be compression or crypto or whatever, cryptography or anything like that. Even the key element is that all of these streams allow chunking the work in like a set of buffers, and you can pause and resume them such that when you are in a situation where the source is producing much more data than it can be consumed, the stream can be paused and you can avoid like overflowing or going out of memory, running out of memory, and things like that. This is typically referred to as like back pressure. So the abstraction is, as you can imagine, there is like a readable stream and there is a writable stream, which is, one is the source, the other is the sink. The difference with Node.js, actually the biggest one, other than this being done in C++ and not in JavaScript, is that all of the buffers that are going to be used are part of a pool, and you can never exceed this pool. So that's like one of the key design constraints. And this allow to define like a region of memory where the async stream should live, and you are sure that they will never be allocating anything outside of that, which is going to be very handy. You can build duplex streams, which is like a mix of readable and writable streams. And we have been implementing this transform stream, which is a state machine. All of these are, more or less state machines that is coordinating the transformation of a buffer into something else. So the difference between a duplex stream and a transform stream is that the transform stream is producing new buffers from the input ones, while the duplex stream, potentially the reading and writing side are unrelated one to each other. And last but not least, we have this async pipeline object that is coordinating multiple writable streams with a single source stream, potentially multiple transform streams. And it's, a pipeline, so it's routing things and making sure that everything goes to the wanted destination. I have implemented this first this synchronous zlib transform stream, which is taking the input buffer and transforming it using zlib, so basically compressing it and uncompressing it. And it's very simple when you try to do it in a regular synchronous way, which you can read. It's even very, very few lines of code, and it's handling even like the trails of data when you have to finalize a buffer. So it's pretty compact. Then this synchronous code has been transformed into an async state machine, which is called async transform stream. And you can see it here. You can see it's a state machine because it has this state that will change depending on what's going on in which phase you are in when transforming the data. But the actual implementation of the zlib is still just doing synchronous zlib transforming into each one of the callbacks, which one is called onProcess. That is the callback that needs to really compress the data and do the actual compression work. And the other one is the onFinalize, which is the one called when there is no more input data and we just want to finalize the stream. So writing any trailer header, any training data that is needed by the compression stream. Sometimes you have CRCs and things like that. So that's what this method is for. Can be even invoked multiple times because then the actual finalization is controlled by this stream-ended flag. So let's try to first verify that what I'm saying is true. So let me open the test. So sc test as always, and I need to remember doing this before starting the stream, but that's all right. Let's just do run async request stream test, because this is the test we would like to be using to do what we need to do today. This test is basically, well, this is described. Sorry. We are writing like a file and creating a readable stream out of it. So we write a file with some expected data. We create a readable stream out of it. We route this into transform stream, which needs to be somewhere. Transform stream. Here we are. It's this zlib transform stream, which is going to then be routed to a socket. And we have two sockets connected. So this is, traveling through the network. And on the other side, the socket receives, it decompresses the data using another transform stream, and it's writing it to this syncs, which is a writable file stream, which is again a file. It looks very not smart if we don't want to be using another word, but it proves the point of this library. But now if I try to run this, we can see that we are stopping here into this process and finalize, and we can see that we are on the main thread. Where are the thread? Yes, thread 1. So it's not much of a use to have, we have created this very complex abstraction, but we are still doing work on the main thread. It's, kind of meaningless. Why are we even doing this? So the point we need to do today, to reach today, is to be able to use the SC async library and do all of this work on a thread. To do so, we can use AsyncLoopWork, which is not showing up here because we need to include async, which is the SC async library. Now we should have AsyncLoopWork, async work. Let's try to see what we need to do. So we need to connect this process and finalize callbacks from the, we are deriving from this async transform stream, but it's not strictly required. I'm not using like virtual methods, so you could potentially just bind the callbacks to some Lambdas and get the work done. But as this is a library, it's probably good anyway to keep all of the related variables in a single class. So this is not so much different from using an actual virtual function, but we're going to do it anyway. So let me move this maybe to a method because I don't like using Lambdas other than prototyping. So how can we call this? I don't know. We started with the, I don't know. Compress process and compress finalize. Yeah. What parameters do we have? We have for the process, that's what we have. And for the finalize, that's what we have. Let's put it here. Now I can replace the lambdas. Let's see async slib transform stream compress process. And this is a void. And let's copy it and create also the compress finalize that only has the output. So you see the process has inputs and output. This is coordinated by the async transform stream state machine. It's saying, hey, I'm giving you this input. You need to process it into an output, but you can do it asynchronously because I will consider this work to be done only when you call this after process, and that's the key. But for now, this is returning results, so they cannot be void. Let's do result. Yeah, because they need to signal if something is going wrong. I can move this into the process, and I can move the other one into the finalize. This is not compiling because, of course, this is wrong. I need to change the result type to be SC result here and SC result here. Beautiful. Now, on process, I can bind to async delete transform stream on compress process with this no matching member function because I need to take the address. And I can do the same for the finalize. Finalize, it's going to be compress finalize. All right, this looks decent. Let's see if this is still working. Maybe removing the breakpoints. Yeah, this is still working. Okay, what's the next step? Now we need to connect. So the idea is we need to move this work into a secondary thread. And we have this async work. Async work is an object. Let's see. Let's look at it from the async library that can run a work callback into a thread pool, which is, just a bunch of background threads. But the cool part is that it has a callback that will be invoked on the event loop that this object is associated with, is started on. You can start this async object into this event loop. And this is handy because it greatly simplifies all of this, bookkeeping to avoid any kind of deadlock or anything like that between threads. So we have to bind the work callback, which is just an empty function with no arguments returning a result, and the actual callback, which is returning a result. Actually, these are two different result objects. This is the SC result, which is the regular just return code type of object, while this result is an alias for this async result of AsyncLoopWork, which is basically AsyncLoopWork double colon result. So sorry for the confusion. Maybe I should rename these two objects, but for now, we are going to survive. Let's bind them directly to some callbacks. So let's call one work and another one after work, which is async loop work result. I guess that, I know this library in every single line because I have been working on it for quite some time and writing basically all of it. And it's really nice when you are touching code that you own with this level of know-how on the insides. But yeah, it really makes me happy. So I guess that's why I'm continuing to do this. So async work, we need to bind it to async zlib transform stream and async zlib transform stream work. Always on this object. And we want to be binding also the after work on the after work. No member named after work. Why? What am I doing wrong? Oh, I have not declared it. It's here. Oh, after work, callback. Yes, sorry. Return result true. Okay. So the idea is that the after process is called here in the after work, but we need to save the input and output from, when it's getting given to us, when we are given the input and the output into this compress process. So let's save it. We need basically two variables. And the cool part about the state machine is that it guarantees us, it's giving some guarantees that we will not get the compress process called again until we are not communicating that we have been processing the first set of input data into some output data. So we can definitely do this. So saved, let's call it saved input, right? Saved input, saved output. So this is our input, saved is our output. We don't want to be doing the process. Process needs to be done here on the saved input and save into the saved output, right? And the same also here, right? Okay. We need to do the same for the finalize. So also here we have a finalize, and we need a way to distinguish, right? So when we are finalizing, we need to distinguish the case when we are finalizing from the case where we are just processing. So my first reaction is to do if finalize, I don't know. Finalizing, we finalize, otherwise we process. Finalize also needs this stream ended flag, which we are going to declare also here. So you see, when taking something that is synchronous and making it asynchronous, you have to take all of the local variables and putting them into somewhere, some place where they persist, and you can recall them later. That's more or less what the async await mechanism is doing, but it's doing it in a way that is automatic, and it's not visible. It's not like you don't have like a clear control, and you are risking of allocating a lot of stuff on the heap without noticing. So that's why doing things this way with manual state machines, async state machines, it's definitely a lot harder to reason about, but it's it can be more efficient. And I wouldn't suggest to do this for application level code. So probably application level code is fine to be using async await, co-async and co-await would be in C++, but for library code that needs to be very efficient, I prefer to use like actual state machines. So finalizing, we need to set the finalize, well, probably also the after finalize needs to behave in a similar way. So if finalizing, we do after finalize, otherwise we do after process. And we need to use the saved output, right? So compress finalize, we need to save the output, the input. Now it's basically empty. And finalizing is true, while here finalizing is false. I mean, it's false by default, but I guess it doesn't hurt to set it to false anyway. Okay, we need just one more thing, because for now, nobody is going to be calling this work until we start the async work, right? So async work, start, we need the event loop. I don't know if I will be changing this, but for now, I'm always assuming that someone is calling the, it's called like cache event loop. It's really weird name because I don't know. I want to make sure someone is passing the event loop on the start, but at the same time, it's handy to have a start overload where the event loop is already set. So I have this get event loop and I have a cache internal event loop that some caller, some user of the library can use to avoid needing to pass the event loop on every single function. So for now, that's how it works. I don't know if I will be changing it, but yeah, that's going to be fine for now. So this looks good. We are binding the process and the finalize into these two functions, saving the inputs and the outputs, making sure to remember if we are finalizing or not, and starting this async work, which is going to execute the work callback on another thread. On this thread, we will be doing the actual bulk work of, actually it's zlib doing the work. We are not doing anything other than using this beautiful library. And after processing our output, then we are communicating to the event loop, actually not to the event loop, to the async transform stream state machine that we have processed some data, or even that we have finalized, potentially even ended our stream of data. Let's modify now the, I think that this should be fine. I think what we need to do now is modifying the async request streams test, which is not this one, it's this one. And this test is always getting longer and longer. I need to clean up. I need to clean it up a little bit at some point, but not now. I know, and I already know that I have said this multiple times, but you will see at some point some git commit where I will be cleaning it up. So let's create a trade pool with two threads. So we have our thread pool. Where are the transform streams? Here we are. Yeah, you really need to set way too many things here, but this is more an API that needs to be cleaned up and maybe adding some helpers, but for the sake of the test, this is going to be fine. So this is the first transform stream. So we have now our async work field. This async work field, we need to definitely cache internal event loop with the event loop. and we need to set its thread pool. Set, maybe we'll set debug name as well, compress stream. And what else do we have? Set thread pool, yeah. And if this can be failing, we need to make sure it doesn't fail. This sounds good. Let's do the same for the decompress stream. So you see, we are not really doing a lot of work here, but I wanted to, record this into a video to somehow close this work on this async streams, because I suspect I will pause it for a while because I have some other plans on what to work next. So this is really trying to close a cycle. I think this looks good. Let's try to run this. Let's see if we are even getting into the work callback. We are getting in the work callback, and as you can see, we are not on the main thread. So this is just very, very nice. Excellent. Let's see if this is running. Oh, this even runs and works. And that's really amazing. What else can I say? So let's recap again. What I have been doing in this entire video is basically making sure that the work that is doing the actual compression, as you can see, we are going into the stream process, which is going into zlib and actual calling zlib deflate. Let me put it here so you can see it. And it's calling deflate on the actual zlib DLL. This is done on a thread that is a secondary thread that comes from a thread pool. You see, thread pool worker. This is very cool because what we are doing in the test is something like, let me try to, yeah, maybe I should add a comment here. It's like file stream, and then we have, oh, well, it's already here. We have a file stream, we have a compression stream, and we have a writable socket stream. But now this is an async AO. Actually, I think this is even running on another thread pool, because for buffered files, you cannot really do async IO. This is running on another set of thread pool, and this is using async IO. So it's not using any thread pool, but just the event loop facilities to register a socket and be told by the operating system when some data arrives, or it's finished writing, in this case, to the stream. And the same on the other side. So this allows us to keep basically all of the cores that we have decided to dedicate using the thread pools occupied with compressing and pushing data as fast as you can. So this is giving you, let's say, potentially the highest throughput for the system, because the reading, basically you can be reading data from the file stream, but at the same time you are compressing potentially buffers from that have been previously read, and at the same time maybe you are writing some buffer that you have already compressed. All of these operations, they happen in parallel. That's why we are making this building this complex system, and this is why it's so cool. And when I have seen it done in Node.js, I've always been thinking that this would be really cool to redo and make it available in C++, in other languages, and another runtime, if you want, that is doing this kind of I/O operations. What else can we say? I think this is all for today. I achieved what I wanted to achieve. I hope you enjoyed this video, and that you have been learning something, hopefully. I think this video is closing for a while the series on the async streams, because I will be working on SC async directly in the next period, trying to make it more solid. And I really would like to understand if that library can be brought to a level that can be of a general use. And this is all for today. See you next time with Sane C++ libraries.